All right, so this video is for section 5, and it's for the first part of section 5, which I'm actually going to cover two things in it. I'm going to do a picture for glycolysis, and I'm going to do Krebs cycle, right? Electron transport I'll do in a different video. So the reason why we need to do glycolysis is because we actually oversimplified glycolysis in our last picture, right? We talked about this 6-carbon molecule turning into a two 3-carbon molecules, but really what happens in glycolysis, so you have room in your notes for this picture, is you take your 6-carbon glucose, you break it in half to make two 3-carbon molecules, but that's actually not the last step. The last step is you change those two 3-carbon molecules into two pyruvates, is what we call them. So it's pyruvates, pyruvates. And those pyruvates actually have 3 carbons in them, but I gave you a name for those molecules so you would understand that they are different from the original 3-carbon molecule. So this molecule is different than this molecule, and there's more than one step. Before we said there was one step, more or less, right? So that's what's going to change. This first step is actually powered by 2 ATP, which is way different than last time, right? I'm going to take 2 ATP, turn it into 2 ADP, and that's where things get really funky really fast. In the other picture, I made ATP. I made 2 ATP by breaking down that glucose. But actually the first step here, I'm going to have this cost of 2 ATP, and that actually should make sense from other contexts, right? If I go back to chapter 2, when we had pictures like this one or like this one, you knew no matter what, before I can come down, I have to go up, right? I always have to add energy before I can release energy in a reaction, right? I have to input energy to break bonds before I can form new bonds in my products. So whether it's endothermic or exothermic, there was always this certain level that needed to be reached, this activation energy. So that's what we're talking about right here. This 2 ATP that you spend to start this reaction, so I actually go in the hole before I can make any ATP, right? It's going to cost me 2 ATP because I have to get this reaction started, and any reaction has activation energy, so that should actually make sense. So this first step is one of those weirdos. I'm going from 6 to 3. This is actually anabolic because I had to input energy to make it work, right? ATP to ADP is catabolic, so this is definitely an anabolic reaction. The second reaction, when I go from these 3-carbon molecules to pyruvates, that's where I actually get some energy out. That's where I can make my 4 ATP from 4 ADP molecules, and that's where I get back on in the positive side, right? That's where I get back out of the hole. So if I can make 4 ATP here, if I can gain 4 ATP back, that's where my original picture comes into play, right? Excuse me. I'm combining those two things, a -2, a +4. That should give me a net gain that's +2 ATP. So I had simplified that picture originally so that there were 2 ATP being created. I just didn't talk about the cost. I didn't talk about the activation energy. But in reality, when we look at this actual process, it costs us 2 to make 4. That's why there's a net gain of 2 ATP in this process, right? So glycolysis will get you 2 ATP. Glycolysis also will help you make some other energy molecules, right? So I need to create a different energy molecule here that we're going to call NADH. That's actually different than before in the photosynthesis version of this. It was an NADPH, right? Now it's an NADH So they are technically different, but that NAD plus and a hydrogen ion can catch some electrons to make this NADH molecule. And those electrons are going to be useful later for me to make more ATP. But this is one of those molecules that I'm going to need oxygen to take advantage of. So anyway, this is a complete picture for glycolysis, as complicated as we're going to make it at least, right? So it's not quite as simple as just break it in half and get to ATP. Technically, I have an activation energy, so it costs me 2 to get 4, get a net gain of 2 ATP. But I'm also going to make these NADH molecules that we didn't talk about before. Those pyruvates now at this point are going to be moved into the mitochondria if we're talking about a eukaryote. And that's generally what we're talking about in this chapter. So definitely going to happen here. So I'm actually going to go back down to 0. Remember, technically, if I spend these 2 to move those pyruvates, my net gain at that point would be 0. So that's my glycolysis picture.